Good afternoon, everyone. My name is AbdulRahman Anas, and today, inshallah, we'll be having a quick review session on stereoisomerism, chapter number 5. Okay. Um, so I hope everyone is doing well, and let's actually start with the session itself. Can you all see my screen, first of all? Can you hear me, Aslan?
Yes, we can hear you and we can see the screen.
Okay, it's okay. طيب. So our topic, as I said, is about stereoisomerism, and we'll start off just quickly with the table of contents. Now, I'm not going to go exactly as the table of contents is organized. I'm just going to go on my own flow. It will cover everything that is in the table of contents, but yeah, just don't take it as a reference point for how you'll navigate through with the PowerPoint itself. Okay, so let's start actually with the topic. The first topic is chirality and enantiomers. So guys, what do you know about, let's start with a quick question. What do you know about isomers themselves? Just the basic definition of isomers. Just open your mic and speak up.
Same proton number, but different nucleon number.
Again?
They have the same proton number, but a different nucleon number.
No, these are isotopes. I'm talking about isomers. Anyone?
Different arrangement.
Okay, but what's the other condition?
Attached with the same number of atoms.
That's exactly it. So they have the same molecular formula, but a different arrangement or a different structural formula. Okay. So at the end of the day, there are the same. There are the same number of atoms in those molecules, but we'll have different structures when it comes to the actual molecule itself. Now, what about stereoisomers? What do you know about stereoisomers? What's your own idea of stereoisomers? Anyone?
Has different orientations in space.
Okay, so they have different orientation in space, different spatial arrangement of atoms. Okay, but at the end of the day, they are the same they are the same molecules, right?
Yes.
Okay, so now do any of you remember any certain classes of stereoisomers? I think you actually took them in chapter 2 and chapter 3.
Conformers and configurational isomers.
Okay, that's correct. So conformers and configurational isomers. So, okay, we'll move on with the PowerPoint. As we said, stereoisomers are the property of a molecule or molecules having the same order of attachment, but different spatial arrangement of atoms. So how they are oriented in 3D space, الفضاء بشكل عام, and how we look at them will differ depending on our own point of view. Okay, but inevitably, they are the same molecules. Now, you've mentioned that there are two classes, okay, and we'll just quickly go over what are these classes. Now, we said conformers. Now, conformers can be interconverted by rotation around a single bond, okay, and they'll always have the same connectivity sequence. But again, we can actually rotate them without breaking the bonds. But in configurational isomers, we'll have to break the bonds. And if you know the reason why we'll have to break the bonds, why do you think we have to, first of all, break the bonds, then reform them into their new conformations or configurations, let's say?
Because of the double bond?
Exactly. It is because of the double bond. The double bond creates a strong enough force to restrict the rotation of the let's say the atoms in the molecule itself. So we'll have to actually first break the double bond and then reform the bonds in the new configuration or in the new rotation. Okay, so we'll move on to our the next slide. Okay, So this is just basically a mind map just for you to be guided around and differentiate between the different types of isomers. We mentioned stereoisomers. Now, if you remember that we had constitutional isomers, and the difference in the functional group, the difference in the positions of the functional groups themselves, the difference in the backbone of the let's say the compound. Okay, and these are just the basics of isomers. Now, our topic for today is stereoisomers. Now, you've supposed to, I think that you've done conformational isomers in chapter 2, the cycloalkanes, the alkanes themselves, and so on. And today's topic is going to be about configurational isomers. Now, we'll go over the cis-trans isomers, the geometric stereoisomerism, but in a new way. It's called the EZ convention or the EZ method. Okay, but our main focus today is going to be about optical stereoisomers, okay, which are either diastomers or enantiomers. And there are mesocompounds, which are basically diastomers, but with special rules. And yeah, that's basically it for today's topic. Now we'll move on to chirality. What do you guys know about chirality?
And a carbon is a chiral center if it's sp3 hybridized atom and it's connected to 4 different substituents and there's no line of symmetry.
Okay, that's true. Now, I'm sorry, I didn't catch your name because I have like multiple tabs open. Anyways, so basically what your friend was trying to say is that in order for a compound or a molecule to be chiral, we must have a stereogenic center. A stereogenic center or a chiral center or a stereo center, they have multiple names, we'll go over them. Is basically a carbon atom in organic chemistry with 4 different groups or ligands attached to them. Now, in order for it to be attached to different ligands or groups, it must be sp3 hybridized. Now, in definition, a chiral molecule are molecules that exhibit the property of handedness. Okay? And what do you think is the opposite of a chiral molecule? Chiral is?
A chiral.
Chiral. That's correct. طيب. Now, one certain property and one certain, let's say, characteristic of a chiral molecule would be is that it cannot be superimposed. What do you mean by superimposed?
Identical image.
Okay, an identical image. Any other ideas about what's it called? About superimposable images?
Yes. Can I?
Yeah, speak up عادي يعني. not just-
Yes. The mirror image of a certain molecule can't be in the same places in the space.
True. So basically, what your friend was trying to say is that you cannot restack the different parts of an object over each other. Like the mirror image cannot be stacked over or put on the original object itself. Now I'll give you an actual example, an actual demonstration. Let me just open up my camera. Now, just before I open up, it's the property itself is called handedness, and I'll show you where this word comes from basically, and how they actually explained it. So hi everyone, this is me. Wait, yeah, okay. So hi everyone, this is me. Okay, so assuming this is a mirror image of my hand, okay, what you see is the mirror image. Now this is my left hand. What would be the orientation of the left hand of my image? Would it be right or would it stay left? Hello.
It will be right.
It would be right, exactly. So if I was to take my right hand, okay, this is the mirror image, assume that this is the mirror image, and stack it over my left hand, would they be superimposable?
No.
No, they are non-superimposable, right? And so this is basically the concept of handedness and concept of chirality. I can say that my hand is chiral, okay? Because whenever I stack up over it the mirror image of my hand, they'll never be superimposable. Unlike, let's say, a ball. A ball, however we orient it and however we place it on, like in front of the mirror. The mirror image will always be superimposable over the actual object itself. Now, I need you to memorize these terms, especially superimposable and non-superimposable, chirality, chiral molecules, and achiral molecules. These are really important for your understanding and for the test itself. Yep. Okay, so we'll move on. Any questions before we continue? And just in case, I know I'm moving fast, but it's just because of time. Everything is clear?
Yes, everything is clear.
Right, okay. So we'll move on to, wait, let me move on with the slides. As we mentioned, chirality in definition is a chiral molecule, or chiral molecules are molecules that exhibit the property of handedness. I showed you the example of the hand and then the ball. Okay, now a molecule that can be superimposed on its mirror image is a chiral molecule. I'm sorry, just 1 second. Okay, sorry everyone. I'll just go on again. So we've mentioned that a molecule that cannot be superimposed on its mirror image is a chiral molecule. A chiral molecule, meaning that it is chiral. Now the opposite of chiral is achiral, and we've mentioned the ball, I think. Okay, the ball example. Now let's talk about actual molecules. Okay, so what do you think is the difference between those two molecules? I mean, what causes? Just mention out everything that you see is different between those two molecules. There's basically one main thing, yeah, okay, whatever you can see, whatever you can tell me.
That the carbon on the right is connected to 4 different molecules or groups, while the one on the left has like a copy of the same group. Yeah, it has 2 CH3.
That's correct. So basically, what your friend is trying to say, the molecule on the right is a chiral molecule with 4 different ligands attached to it. And with this being said, now what about the plane of symmetry? Assuming that I have a line going exactly through the middle of the molecule itself, which one of those two would have a plane of symmetry?
The one on the left is superimposable.
Okay, the one on the left is superimposable. Okay, before we go into the plane of symmetry, what do you know, guys, about the plane of symmetry or the mirror plane? Any ideas?
Like if we have a certain molecule that have like three different, not four. If like I put it in a certain way and cut it into 2 halves, I can see that this side is mirror for the other side.
Okay, that's basically the correct concept of a plane of symmetry. Now, you've mentioned that we need to have 3 different ligands attached. So, in other words, we need to have 2 ligands, okay, of the 4 ligands attached to be the same. Okay, so in total 3 different ligands, but two of the 4 ligands should be the same. Now, a plane of symmetry, when it comes to talking about the definition, is an imaginary plane, an imaginary line. Okay? And so this line would pass through the center of the molecule, through the middle, and it will divide it into 2 halves. Okay? And I'll take the example of the next slide. 1 second. So yeah, as you can see, now this is the wedge and dash representation of this molecule. Wait, sorry. Okay, of this molecule over here. And so if I was 1 second. Can you see my cursor, by the way? I don't know if you actually can see it or not.
Yeah, we do.
Again? Sorry.
We do.
Yes,
We can see it.
Okay, fine. Okay, so you can see the molecule itself in the wedge and dash representation. Okay, and we have a plane of symmetry, an imaginary line that passes through the dead center of the molecule itself. And so this line itself would separate the molecule into 2 parts, into 2, let's say, 2 mirror images, right? Okay, and so this property itself, the ability for a molecule to be separated and divided into two parts, and these two parts would be mirror images of each other, would identify a molecule as being achiral, not chiral. Okay, so because chiral molecules would have no plane of symmetry, and we can see this in the previous slide. If you look at this molecule, at the molecule on the right, you see that there is no way that we can have a plane of symmetry, which is, as I said, a property of chiral molecules. But on the other hand, the other molecule um, can have a plane of symmetry, and thus we can consider it as achiral. Okay, so we'll move on. Now we've discussed the stereogenic center. Okay, one of your friends have correctly explained it, so we'll go quickly through it. Wait 1 second. Okay, before we go through it, we'll talk about enantiomers. طيب. What are enantiomers? What do you think enantiomers are?
Two molecules that don't have a superimposable image.
Okay, a molecule that doesn't have a superimposable image, a non-superimposable image. That's true. طيب. And how many enantiomers would you expect a chiral molecule to have? And in general, with one stereogenic center.
2.
Is there two enantiomers? That's correct. طيب. Now, when it comes to the properties, what do you expect the properties to be of these two chiral molecules?
Same physical and chemical properties.
Again, sorry. I
Same
couldn't.
physical and chemical properties.
So in general, okay, in general and virtually speaking, they should have the same chemical and physical properties. Now, there are some exceptions and there are some cases where they'll behave differently, and we'll discuss them later on, okay, at the end of the chapter. But for now, in general and virtually, we say that they have different, they have almost identical properties. Now, to expand further on this, we'll say, and more specifically, we'll say that they have identical achiral properties and not just chiral properties, because saying that physical and chemical properties will include everything. Okay, so we'll say that they have identical achiral properties. Okay, but why do you think they'll only have identical achiral properties? Yani, what is your idea behind it?
إنه they interact different يعني مع biological لأنهم chiral.
Okay, fine. So what you're trying to say is if they interact with other chiral molecules, let's say, or other chiral substances, they should behave differently, right? Is this what you're trying to say?
Yes.
يعني فرضا إنه عندنا chiral substance تاني طيب, and these two substances, two different substances are both chiral. If they ever interact, إذا بتفاعلوا مع بعض, الانانشيمر الثاني تبع الفيرست chiral substance would have a different reaction, صح ولا لا؟
أيوة بفرق.
Okay, now this is true, but what I'm trying to get you guys to understand is why do they have identical achiral properties? Okay, I'll quickly give you an example. طيب. Now, assuming we have a pencil, now this pencil is considered a chiral object. Do we agree on this? Before we continue.
Yes.
Okay, so and we've mentioned that our hands, the right and left hand, are both chiral objects per se. Okay, a person that is right-handed would be able to use this pencil, right?
Yes.
And the person that is left-handed will also be able to use this pencil. But a right-handed person would usually not be able to use his left hand to write. And this is something also that applies to a person that is left-handed. He wouldn't be able to use his right hand to write. And so with this concept, we understand that now a person with one chiral property in one hand, his ability to write, he wouldn't be able to do it the same on his other chiral hand, which has, let's say, different properties with the same, again, a person with one chiral right hand would also be doing the same thing as another person with a chiral left hand. They'll both be able to write with the same achiral pencil. Okay, so when it comes to achiral properties, it will always be identical. Do you get do you get the example that I'm trying to get you at?
Can you repeat it?
Yes.
Okay, طيب.
Can you
Now,
repeat it?
طيب, okay, again. Now we've mentioned that a pencil is achiral. It has a superimposable image. It doesn't have, let's say, the mirror image would be stacked over it perfectly. طيب. And then we have a right hand and a left hand. Now, assuming that we have a person that is right-handed, he would be able to write with his right hand, صح? And use this achiral object. But this right hand is chiral, صح ولا لا?
Yes.
The same thing would apply to a left-handed person with that would need to write with his left hand, صح ولا لا?
Yes.
He would be able to use the same achiral object, صح ولا لا?
Yes.
So this is the basic principle or the basic idea that I'm trying to get you. Now, mentioning that they have identical achiral properties, whether that be melting point, boiling point density, solubility, and more, and many more. طيب. So do you get the point?
Yes.
طيب. Now, there are different chiral properties. Again, let's get back to the example of the hands. If you have a right glove, which is, let's say, a chiral object, would you be able to wear it on your left hand?
No.
You wouldn't be able to. And the same would apply with a left glove and you wouldn't be able to wear it on your right hand. And so with this concept, chiral objects would interact differently with each other. And the enantiomers of a molecule would interact differently with other chiral objects or other enantiomers, let's say. طيب? This is another point that you have to understand. So basically, they have identical achiral properties in simple words and different chiral properties, which we'll discuss real quick. And we'll discuss further on during the chapter. طيب. As I said, enantiomers are a pair of molecules that can be superimposed on each other. Now they have identical achiral properties, whether that be melting point, boiling point, or density. Now I've also mentioned that they have different chiral properties. One of them is the optical activity, and we'll talk about it later. And the other one is how they interact with other chiral molecules. And there are two rules that we'll discuss at the end of the chapter. Okay, is everything clear so far? If you have any doubts, just tell me, so I can clear them before we continue. And this chapter is quite confusing, so if you don't understand, please tell me. All good?
Can we associate having enantiomers as chiral properties? Like the chiral compounds or structures can be always considered enantiomers?
Okay, yeah. At the end of the day, enantiomers are chiral molecules. Okay, they are a pair of chiral molecules. So we wouldn't say that enantiomers are a property of chiral molecules. I'm not sure of this, but we can say that enantiomers have the property of being chiral. Okay, it's the opposite way.
Oh yes, okay.
Right? Okay. Because certain enantiomers wouldn't be chiral. We'll discuss them later, I think, in mesocompounds. Okay?
Yes.
طيب, now we'll talk about stereogenic centers. We've mentioned them. طيب, we've mentioned that other names, stereogenic carbon atom, chiral carbon atom, are just a chiral center and simple. And definition is a carbon atom with 4 different groups or ligands attached to it, giving rise to stereoisomerism. Now, in order for this carbon to have 4 different sigma bonds, it has to be sp3 hybridized. Any of you guys remember what's the angle and the geometry of an sp3?
109.5.
And the geometry?
Tetrahedron.
Tetrahedron.
That's correct. Okay, so we'll move on to one of the biggest topics in this chapter, the RS convention. Okay, before we start, what is a configuration? What do you think is the meaning of a configuration? And you think about it as the ligand, the ligands attached to the stereogenic center. No idea? Okay. Now configuration is considered, we can say it is the arrangement of the groups or ligands attached to the stereogenic center. Okay, so it's basically how are the groups or the ligands attached to the center carbon, and in what order or in what sequence. Now, enantiomers themselves, what do you think, would have the same configuration or different configurations?
Different.
Yes, they'll have opposite configurations to be exact. طيب. They'll not be the same because at the end of the day they are mirror images. صح ولا لا؟ طيب. Okay, now one method is to identify or specify the configuration itself would be the RS convention. Okay, now it's actually taken from the Can-Ingol pre-log system, and there is another extension to it, which is the easy convention that we'll discuss later on. But let's stick for now to the RS convention. طيب. What do you already know about the RS convention? Real quick.
That it could be either a clockwise or a clockwise attachment or configuration.
Okay, that's one thing. So it's either clockwise. And what is the letter that we use to denote that this is clockwise?
Clockwise, I think, is R.
Okay.
And counterclockwise is S.
That's correct. طيب. So basically for the RS convention, now this is a method that we use to describe the way the ligands are attached to the center carbon. And this depends on one thing. طيب. The way that we number them depends on one thing. What do you think it is?
Priority.
Atomic
Priority. And what is priority based on?
Atomic number.
Atomic number. Okay. So we've said that ligands attached will depend on their priority order, and this priority order will depend on the atomic number. We've also mentioned that a clockwise array or a clockwise configuration is denoted by the letter R, and a counterclockwise array is denoted by the letter S. طيب. Now we'll discuss this basically. Can you see the image on the screen? Let's discuss this quickly. What do you mean by clockwise and counterclockwise? طيب. Now this is a molecule, a compound that we have. Okay, and they're starting from the letter B, with A being the lowest priority since it's at the back. Okay, whenever we're writing down the RS convention, we'll try our best to keep the lowest priority group in the back, or like excluded from the counting to make it simpler for us. In the back, that means we'll have the dash, let's say, drawing attached to the lowest priority group, which is in this case our A. Again? Sorry. Okay, fine. I thought someone was talking. Anyways, as you can see, we have one image, or let's say the actual object, being clockwise, while the other is a counterclockwise image. Okay, so the first one would be assigned the letter R, the other would be assigned the letter S, and this is basically how the array is, let's say visualized here. طيب. We'll talk more about it and how we'll actually have the RS convention done, and then we'll move on to the easy convention. Okay, so basically we've mentioned that it's the way to describe the way or the array in which the ligands are attached, depending on their priority order, and this order can be either can either form a clockwise array it is denoted by the letter R, or a counterclockwise array denoted by the letter S. And the priority is always determined based on its atomic number. Now, there are certain rules for the RS convention. The first is, as we've mentioned, the priority itself. Higher priority to the highest atomic number atom, or the higher atomic number atoms. And the second, and the priority would move on, and we usually have H as the lowest priority always. And if H isn't present, hydrogen isn't present, we'll just look for the lowest priority group and assign it the number 4. طيب. Now for the second rule, I'll keep it simple. These rules, you'll have to remember them. There's nothing that I can ask you about. طيب. Now for the second rule, it talks about how atoms are, how we determine which, let's say, if we have two or more atoms that are directly attached to the chiral center itself, okay, how do we actually determine which atom do we take or which group do we take if the first atom of these two groups is the same? Okay, so in this case, we'll just move on outwards from the stereogenic center and until we reach a point at which the two atoms would differ. Okay, and in this case, we have the ethyl group. The first carbon in the ethyl group and in the methyl group is the same. So, and the attached, let's say, subgroups or the attached hydrogens are also the same. And so we'll move on to the next carbon. The next carbon is compared with the hydrogen over here, and then we spotted the difference. This difference would confirm that the priority would first go to the ethyl group and then to the methyl group. And now for rule 3, okay, it is when we have multiple bonds. Okay, now I know this is quite confusing, but shall I make it simpler for you? So basically, it talks about whether we have either double bonds or triple bonds. And this can be also used with aromatic or aromatic rings. Now they say what is mentioned over here is they are treated as if they are an equal number of single bonds. Now we'll exclude one bond from how I do it is that I'll exclude one bond from the, let's say, double or triple bonds, and then I'll look at the next atom and just add extra bonds, as you can see over here, of the same atom itself. So the first one is C triple bond CH. You can see that it's a triple bond. I said we'll exclude one bond and then basically just add for the first carbon 2 other carbons attached to it. Okay, and for the second carbon, I'll do the same. Do you get what I mean? Or is it
So I will
confusing?
make it like it is attached to the 3 carbon.
Yeah, it's basically attached to 3 carbons. That's basically it. Yani the original carbon, that is the CH. Okay, and then 2 extra carbons because of the 2 extra bonds, other than the first sigma bond. Okay? Do you get it, or should I explain it further?
Could you please repeat it?
Okay, fine. Let's see if I have a pen. Okay. So basically over here we have 3 bonds. Can you see it?
Yeah.
Yes,
Okay.
I can.
Okay, with these 3 bonds over here, okay, we'll look just at the side. We'll cancel. What I do is I'll cancel the last bond because this is the sigma bond that is already attached to one carbon, and I'll have 2 lines over here, 2 bonds. I'll just add one over here and one over here, and I'll just look at this carbon over here, at the next atom. Whatever it is, I'll just add it over here and over here. Simple. This is for the first carbon. I'll do the same thing on the other carbon itself. And I'll repeat for the second carbon. Sorry. Okay. I'll do the same thing with the other carbon. I'll just exclude one of the bonds. Look at how many bonds are left. Okay. Add them on the other side. Then look at the adjacent atom to this atom over here, and then just add it as it is over here. Do you understand it now?
Yes, it's clear.
طيب. We'll do the other one just to make sure that everyone gets it. Okay. So basically, what would be the first step that we'll do in order to add, let's say, the new single bonds over here? What's the first step?
Exclude the first bond.
Okay, exclude one of the bonds. We're left with one bond. Okay, this bond will be added over here. We look at the adjacent atom. We just add it. That's basically it for the first atom. We'll do the same thing for the other atom. We just exclude one of the bonds. and then look at the main atom over here that is in the backbone of the molecule. We'll just add one bond and then add the atom itself. Is it clear for everyone? If anyone doesn't understand, I'll explain it again. No? خلاص? Is it fine?
Yeah, it's clear.
Yes, clear.
Okay, so we'll move on to the next. Okay, laser pointer. طيب. So basically, we'll talk about how do we apply the RS convention itself. طيب. Now, before we go on, now for rule 3, we'll just look on, and we'll just, again, we'll go back to, once we've done rule 3, we'll apply again rule 2. We'll just go outwards from the bonds and look at the attached ligands and just compare each ligand with the one having the highest priority, should have the highest atomic number, basically. طيب. Now, for applying the RS convention, okay. Applying the RS convention. Now, as I said, we'll apply, first of all, we'll assign the priority of the attached groups or ligands, and then we'll look at the stereogenic center and decide the lowest priority group. We'll try our best to keep the lowest priority group in the back on the, what's it called? On the dashed arrow or the dashed segment of the wedge and dash diagram. طيب, and then we'll determine the array of the 3 other groups, and we'll just decide whether it's an R configuration or an S configuration. طيب, from what you already see, from the steps you see, can you determine the first one, this one? Is it an R or is it an S configuration? عادي, take your time. طب, okay, let's do it together just for the sake of time. طيب, what would be the first priority? Yani, which ligand or which group would be the first priority?
O,
Again?
oxygen.
The OH group, right? The oxygen over here. Okay, so this is priority number 1. Second priority would be 2.
But are you writing anything?
Yeah, I'm writing on the
I
screen.
think your screen is.
اعتقد الباوربوينت معلق.
Yeah. What screen is it stuck on? على أي صفحة واقف؟
Rule 3.
طيب, rule 3.
It's actually working now.
ظبط؟
Yes.
طيب. Applying the RS convention, again, we've mentioned that we set, first of all, the priorities of the attached group, then look at the stereogenic center from the side opposite to the lowest priority group. We'll determine the array or the priorities again, or let's say the array or the configuration of the 3 groups that are attached, and then we'll decide whether this is R configuration or an S configuration. Type, can you see the PowerPoint itself again?
Yes.
Yes.
طيب, okay. This example over here. Again, what do you think? Is it an R or an S? With the reason, and give me the reason.
You must first put the priority.
Okay, priority. طيب, what is the priority? Give me the order.
OH will be number 1.
Okay, OH.
CH will be number 2.
Okay, CHOO.
Methyl will be 3.
Methyl is 3. طيب, can someone mention why is CHOO the second in priority?
Because we say that we will go to the next carbon, to the next atom, because 2 and 3 have carbon. Number 3, which is methyl, has H, and 2 has O.
So basically, we look at the first difference that we spot. Now we've mentioned that we'll apply rule 3 for double bonds and triple bonds. صح ولا لا؟ طيب. Okay, so basically it's a CH double bond O. Applying rule 3 would give us C H H O attached to O with a C. Is that correct? صح ولا لا؟ طيب. With this being said, يعني, okay, we look at the first difference. This is the CH3 group, so it's basically attached to three hydrogen atoms. The first difference is this oxygen atom, and so the priority would be to the CH00 group. Is that clear?
Yes.
Yes, okay.
طيب. So basically we've done the priorities, and naturally the fourth priority would be to the hydrogen, being the lowest priority group. What about the configuration? What do you think is the configuration of these groups?
R.
R. شو اسمه? Clockwise.
Why is OH number 1? Shouldn't it be CHO because it has a higher atomic mass?
We look at the atomic number, not the atomic mass. Atomic number means the number of protons that are present in the atom itself. Which of both? Will the carbon have a higher atomic number than the oxygen?
Oh, okay.
Okay, so basically it is the atomic number, not the atomic mass. طيب. Oxygen would have a higher atomic number, and so it would have the priority over the CH00, which has a lower atomic number. Only the carbon itself. We look at the carbon and not the whole molecule. Okay, it's only the carbon. Same with the oxygen over here. Unless we're dealing with two, let's say, ligands, not molecules, ligands that have the same first substituent. Okay, in this case, let's say CH3 and CH00 over here. Okay, we'll then apply the second and third rules just to identify whether this would be the first, this would have a higher priority over this or vice versa. So we mentioned that this is an R configuration. Is that clear for everyone? For the people that cannot open their mics, just type in the chat. I can see what you're typing.
Can I ask?
Question.
Go ahead.
اوكي هلا دكتور نجار explained انه احنا دائما بناخد clockwise واذا كان increasing S واذا decreasing R. طب هلا هو ممكن يسأل إشي عن الكونسبت بتاع clockwise او counter clockwise لانه خلص يعني
أنا ما بتذكر كان يسألنا أي أسئلة إنه explain the concept of the RS convention. كان يجيب لنا أسئلة. كمان إذا بتحبوا تتأكدوا من شهد وخالد معنا هلا في الكول. ما كان يجيب لنا إيش ال RS convention as إنه explain the concept itself. طيب. He'll just bring on the molecule and ask you to define whether this is an R convention أو S convention. وصلت؟
Thank you.
تمام. طيب.
سؤال.
تفضل.
بالنسبة لل CH double bond with O wouldn't the C be have a single bond with an O, so their atomic number would be 16 plus 14.
مش 16 plus 14. احنا الاتوميك نمبر حكينا اللي هو number of شو اسمه protons. صح ولا لا؟
صح.
طيب. again هلا احنا لو بدنا نرسمها تطبيق رول 3. طيب راح نطبق رول 3 اللي هو انه احنا نستغني عن واحد من البوندز وعلى البوند الثاني نضيفه للجهتين. صح؟ طيب هلا هي
صح.
زي هيك استغنينا عن واحد من البوندز حطينا الاو وجبنا هذا البوند اللي استغنينا عنه حطيناه هون وحطيناه هون. تمام؟ طيب هلا ايش راح نضيف فوق السي؟
أكسجين.
اكسجين. وايش حنضيف فوق الاو؟
كربون.
كربون. صح. طيب هلا مقارنة بالسي اتش 3 اللي هي هيك. طيب نطلع على الفيرست كاربون اتوم اللي هي هاي هون 1 وهي 1. طيب متشابهات فيهم تشابه بشكل عام واللي حواليهم فيهم تشابه.
في إنه ال C connected with an H.
طيب هذا تشابه واحد بس في اختلاف بالنهاية اللي هو السي bonded to an O. صح؟
صح.
طيب نطلع على الأو ونطلع مقابلها على الاتش اللي فوق. أي واحدة أعلى الأتوميك نمبر تبعهم؟
الأو ولا؟
الأو. إذا في البرايورتي لمين؟ البرايورتي الأولوية لمين؟
ولا الأو ولا؟
للأو صح؟ فإذا هلا السي اتش دبل او هي راح تكون السكند ان برايورتي بعد الأو، بعد الأو اتش، صح ولا لا؟
تمام.
يا
يعطيك العافية.
الله يعافيك. يعني المهم، طيب هسا we'll move on to the next example. Now this example does not will يعني as you can see just before we continue, what do you know about the wedge and dash شو اسمه diagram or representation? What does the wedge mean and what does the dash mean?
I'm not sure, but maybe one is like front of the page and one is the back of the page.
صح. That's basically it. The wedge represents that it's pointing toward the viewer or out of the page. With dash represents that is pointing away from the viewer or out of the other side of the page. تمام؟ طيب هلا we've said or we've mentioned that شو اسمه lowest priority group will always be pointing towards the back. بمعنى آخر we'll keep it at the dash اللي هو dash arrow. طيب. So in this example what do you think we'll do?
Can I have
أول
a
إشي let's
question?
assign the priorities.
But I have a question.
تفضل.
Can like this dash or this can be for right or left, or it's all it is always for back and front?
It's basically a representation whether it's in the back or in the front. يعني we wouldn't say a wedge and dash would represent whether it's pointing to the left or to the right.
Yeah,
طيب.
okay.
طيب هلا let's start with the priorities. يعني tell me the priorities of these atoms. What would you think is the priority?
OH.
OH is the first priority. طيب.
بعدين اللي هي CC دبل بوند.
اوكي.
بعدين الأثر.
طيب ممتاز. والفورث برايورتي كمان مرة للمسكين. طيب. أيوة. طيب أوكي. هلا we'll talk about اللي هو الأورينتيشن أو اللي هو الconfiguration. What do you think is the configuration of this molecule?
S.
طب why is it S?
Because when you do it without flipping the H, you're actually going to find an R, but then you actually need to put the H in behind, and when you do so, you're going to get an S and not an R.
طيب ممتاز. So basically what your friend was trying to say is that we'll flip one of those شو اسمه we'll flip ال OH مع ال H صح? Just so that we can bring the H to the dash, bringing it basically to the back صح?
Just flip it like this, or we must rotate all the molecules.
هلا you can rotate all of them just so that you can get exactly the orientation you want, or the other method. طيب what you'll basically do. طيب I'll do just a quick diagram. طيب what you'll basically do is this is our H and this is our OH. Okay, this is our OH and this is our ethyl group C2H. طيب we've mentioned the priorities. We've determined that this is 1, this is 2, and this is 3 صح? All clear?
Yes.
طيب.
Yes.
Now what we observe, okay هلا we've done one flip. طيب keep in mind we've done only one flip, which is we switched the positions of the H and the OH. Okay? If we ever يعني شو اسمه since we've done only one flip, we will have a quick and let's say it's a look as being counterclockwise depending on the arrows, but since we've only done one flip, we'll have to convert the R into an S. وضحت الصورة؟
Okay, so if
With
it
one
is was
flip.
S, it will be R, and the opposite.
أيوة, if we only do one flip. assuming we did a second flip اللي هو the second flip would be between let's say ال CH double bond CH2 مع الethyl. If we ever do another flip between those two then it will be على طول S يعني بدون نقاش. طيب وصلت الفكرة؟
Or I can rotate it all so it will stay as it is. If it is S, will stay S.
طيب this is the second flip يعني you'll perform two flips. The first flip is to bring the H to the dash. طيب the second flip is just flipping any other two ligands or any other two groups other than the H.
I have a
وصلت؟
question.
تفضل.
Like, if this molecule was like the H in a place of ethyl, how it will flip
عادي.
between OH and
كانت ال H
what?
مكان الإثايل صح؟
أيوه.
طيب ماشي. طيب we'll go over it quickly because our time is quite tight. طيب. Okay, so basically what you're trying to say is, see, I'll just do a quick double bond. We've said H is over here. Oh, this is our ethyl group, C2H5. صح? OH.
Yes.
This is what you're trying to say. عادي,
Yes.
we'll take this, flip it with this.
Okay.
So this
And
is one
the
flip.
ethyl will stay as it is?
عادي. This is one flip. طيب. One flip would give us will give us the priority will give us the array, but we'll have to use the other opposite array. يعني assuming this will give us R after one flip. طيب this will give us definitely R after one flip. Okay, we'll have to convert it to an S. This is assuming that we شو اسمه did one flip, exchange two positions. طيب if we were to exchange this position مع this position, okay, it will directly give us an S and we'll take this S. وضحت الصورة؟
Okay.
تمام؟
When would you need the second flip?
يعني it doesn't matter, whatever suits you, you can do it. يعني we wouldn't, يعني it wouldn't matter whether we use the only one flip or two flips. One flip, just keep in mind, if you do one flip, okay, or one exchange between شو اسمه, the lowest priority group just to have it on the dash, just keep in mind that whatever array that you get, you'll have to use the other array. يعني if you get an R, you'll have to replace it with an S. If you get an S, you'll have to use an R. فهمتوا؟
Yes.
So if we do one flip, we take the opposite, then it
أيوة,
will
the
be
opposite
correct?
array. أيوة, we'll take the opposite array.
Okay.
تمام? If you do two flips, if you flip two ligands while keeping the H in its position, اللي هو ال dash position after the first flip, okay, whatever array you get, it will be the correct array. فهمتوا؟
If we do two flip.
أيوة, if we do two flips.
Okay.
تمام؟ do you want a quick demonstration of it? Of two flips? ولا should we move on?
Yes.
طيب, okay, quickly. This is the OH. This is اللي هو the H. This is the C2H5. Yeah, and this is the C double bond C. صح؟ كله تمام? We will do the first flip, which is switching between the H and the OH. تمام? Are you all following?
Yes.
Yes.
طيب. We'll just replace these two with each other. طيب. If we only stop over here, بعدين we'll assign the priorities. طيب. We'll get an R convention, صح? But we only did one flip, so it's actually what convention?
S.
S. It's actually an S because we did only one flip. طيب. Like we'll do a second flip. طيب. Let's take, for example, we can take any of these other ligands, اللي هو this one, and this one, okay, without this one, and flip them. طيب. And I'll take this ligand along with this ligand, or this group with this group. تمام? طيب, and I'll flip them. Okay, now we've determined this is an S. طيب. يعني inevitably this is an S. طيب. And I did, so far, I'll be doing 2 flips. طيب, this is the first flip. This is the second flip, sorry. C to H5. C double bond C. تمام? Okay, this is the first, second, and third. If you look at the array, it is now counterclockwise, which will conclude that this is an S convention or an S configuration. وصلت الفكرة؟
Yes.
طيب, okay, let's move on then. طيب, the easy convention. Okay, the easy convention is quite simple. يعني there isn't much to talk about. تمام? It's basically an extension that will help us describe the cis and trans isomers. يعني we'll look at this. Can you see the screen first of all? Is it frozen? Can you see? كله تمام؟
Yes, we can see E and Z.
طيب. An extension of the Kahn-Ingold prelog system, which is used to describe the cis and trans isomers. Now we have these 2 examples. Okay, which of the, how can you actually determine whether this is, for the first one, this is cis or trans, and for the second one, whether this is cis or trans? You can't actually tell, right?
Yeah.
طيب. You wouldn't be actually able to tell. طيب, but if we use the same idea of priorities, طيب, هلا, the idea of priorities is that حكينا the highest atomic number will have the highest priority, صح ولا لا؟ طيب. And the easy convention will use 2 letters, اللي هو ال E, which means, which is in German means integer, which is opposite of each other, with Z, which is zusammen, which is together on the same side. Z would mean that they are on the same side. طيب. وال E would mean they are on opposite side, opposing sides. طيب. So what do you expect from this one? Will it be a Z or an E? First of all, let's put the priorities. For this side, what are the priorities? أي واحد حيكون 1، أي واحد راح يكون 2.
I think floor will be number 1 and chlor number 2.
No,
Chlor 1.
chlor 1.
Chlorism.
Fluoro is 1. It has a higher atomic number. طيب, just quickly, I think the chat has something wrong with it.
Yeah, chat is stopped. You can't talk on the chat.
Was it like this from the beginning?
I'm not sure.
Yeah, from the beginning of the session, we couldn't type anything.
Okay, just a second.
Can you try now, طيب? Is it still the same?
Yeah, it doesn't work.
Guys, I guess the chat is not working for now. So if you have any question, it's better if you can just open your mic. And just raise your hand and open your mic. It's gonna be much better.
Yeah, طيب. Fine, we'll move on. عليك. طيب, I'm sorry guys for the people that aren't able to شو اسمه to chat يعني أو to send messages through the chat. I'm not sure what's the reason behind it. Anyways, so we'll move on just for the sake of time. طيب, we mentioned over here that the first priority over here would be to the CL. What about the other side? The BR and the I. Which of them has a higher atomic number? I. So it's basically, we'll conclude that they are both on the same side. So which letter would we assign them?
Z.
Z, exactly. طيب. So this basically would be Z. What about the other one? From this side, from the CL and the BR, first of all.
No, BR.
BR, okay. What about this side, the other side, with the ethyl and methyl groups?
Ethyl.
Ethyl.
The ethyl group would have the higher priority, صح? We'll use rule 2 of the easy convention. It's basically the same thing, and the priority ideas. طيب, are they on the opposite sides or the same sides?
Opposite.
Opposite, so we'll basically use E, صح? Okay, so this is basically clear, I think, for everyone. Now, anyone have any questions? No? Like, how is it used? Okay, it's mainly used with double bonds, double bond isomers. And we mentioned that they have the same priority rule as in the RS convention. طيب, the two higher priority groups are on the same side of the prefix. إذا كانوا on the same side. Wait, I think I've done something wrong over here. Sorry, on the opposite side. I'll fix this later. If they are on the opposite side, then we'll use E. If they are on the same side, we'll use Z. طيب? Just ignore this. I'll fix it later. Yeah, anyways, so we'll move on. طيب, polarizing light and optical activity. This is the probably the longest part of the whole thing, but we'll go through it quickly. طيب, what do you guys know about the polarized light? What is plain polarized light?
It's a light beam consisting of waves that vibrate in parallel lines.
طيب, that's basically the definition. So it's when we ever have a light beam, and the waves that this light beam will produce will always vibrate in the same direction or in the same plane. طيب. This is plain polarized light, and this can only be achieved by the use of certain material or let's say certain objects. طيب. Whenever the light passes through them, it will only allow for certain light beams or vibration or waves that are parallel to the axis of the substance used. طيب. يعني, look at this quick diagram over here. You'll see that the light has multiple. Now, in reality, it has more than just only two vibrations. طيب. But only the vibrations that are parallel to the axis of the material itself will pass through and give us the light observed on the other side. طيب. Whatever is perpendicular or just not in the same orientation as the axis, it wouldn't pass through. طيب. Okay, what do you think is happening in the middle over here? And why is it opaque on the middle, but on the other two sides it's visible? Any idea? No? طيب. Okay. So basically what's happening is these two lenses, let's say, or these two glasses are both are both polarized, let's say. طيب. So they basically would rotate the plane of the plane of the light beam. Now, these two are stacked over each other in a perpendicular manner. Okay, so what basically is happening is that this would have perpendicular axis, parallel axis, or let's say vertical axis, sorry, and this would have horizontal axis. طيب. So light beams that are traveling in the in the vertical axis, okay, wouldn't be able to pass through this lens. طيب. While light beams that are traveling in the horizontal axis wouldn't be able to pass through this lens. Okay, and so stacking these two lenses over each other would create an opaque region over in the middle. طيب, do you understand? Or should I repeat?
Repeat.
طيب, ماشي. Okay, what's basically happening again? Okay, going back to the first diagram over here, you can see that there are axes over here, or axes, that are blocking certain light waves, which are the horizontal light beams. صح ولا لا؟
صح.
Any wave that is in the horizontal plane is blocked, while any wave that is in the vertical plane that is parallel to the axis of the material used will pass through. صح ولا لا؟
صح.
طيب. What's basically happening over here is that we have two lenses. One lens has its axis and the vertical orientation. So it's basically allowing light to pass that is only vertical to this that is only in the vertical orientation, parallel to these lines. طيب. This will only allow light beams or light waves that are horizontal. طيب. وضحت الصورة؟
إيه.
طيب. So putting these two lenses over each other would create a vertical and a horizontal barrier. طيب. For any light beam that is traveling in both orientations. So it would stop light from passing through. طيب. Not only a certain light wave, يعني a light wave that is traveling perpendicular to the axis, or let's say not traveling over here vertically. طيب. وصلت ولا عيد؟
وصلت.
طيب تمام. طيب polarimeter. What is a polarimeter? It's an instrument that we use to detect optical activity. طيب. Now when it comes to optical activity, طيب, what do you think is the definition of optical activity?
إنه how the molecule يعني هي interact مع الأوبتيكال كيف راح نشوف.
طيب, it's basically optical activity. It's a property of let's say molecules, especially chiral molecules, and it is their ability to rotate plane polarized light. طيب, meaning that شو اسمه يعني we'll see over here. طيب, meaning that they'll be able to rotate the beam that is passing through. Like this beam that is passing through, they'll be either blocking it if the beam isn't traveling parallel to the axis of the substance or the optically active substance, or allow it to pass through the optically active substance as long as the light beam or the light waves are parallel to the axes that are present in the substance that is being used. طيب. An optically inactive substance wouldn't have this feature. طيب, or virtually wouldn't have this feature. تمام. طيب, how does a polarimeter work exactly? طيب, it's basically a simple contraption. Now you've seen that a polarimeter consists of a prism, of a polarizer prism and an analyzer prism. طيب. Now a polarizer. عفوا.
The screen is stuck. ما متعرف.
Again. طيب. Is it fine now?
Yes.
طيب. Now basically, how does a polarimeter work? Now for a polarimeter, it consists of two objects, or let's say two lenses, or two prisms. So the first prism is the polarizer prism. The second prism is the analyzer prism. Now the polarizer prism is the one that will actually create our plane polarized light. طيب. تمام. And this sample tube, before we actually start, would be empty. طيب. The analyzer prism is used to create اللي هو a dark field of view طيب, by rotating the prism, because this prism also will polarize the light, or rotate the شو اسمه will rotate the light beam that is traveling through. طيب. So what's basically happening is when light passes through the polarizing prism in the empty sample tube, it will become polarized. طيب. Now the analyzer prism itself, which is at the end of the of the sample tube, will be rotated. Okay, and this angle is what we call the observed rotation. Okay, is what we call the observed rotation, which we'll discuss later on. So yeah. So what's basically happening is once the analyzer prism at some point of the rotation, there will be no light passing through through the sample tube. It will be completely blocked and the field of vision will be dark. طيب. Now we'll have a sample of the substance. The substance is usually dissolved in a solvent and then it will fill up the empty sample tube. طيب. Once it's filled up, if there is nothing that happens or there is no change in the field of view, it remains dark and no light passes through, then we consider the substance to be optically inactive. Otherwise, if there is some light that passes through the sample tube, then the substance must be optically active. طيب. Do you understand the concept of how this works?
Can I ask you a question?
تفضل.
What kinds of a question that we might face?
طيب. What usually يعني now I remember one question which was a calculation question. I honestly don't remember the other questions that were related, but they're mostly gonna ask you about calculations regarding this. I don't think they'll ask you about the mechanism of how this actually works, and yeah, that's basically it.
Okay.
طيب. Again, بس it's the concept of how a polarimeter works. It's really simple. It's just light passing through, then being polarized by the prism. Then we have the analyzer prism on the other side. This analyzer prism will be rotated until nothing can be seen, no light beam can be seen. Once no light beam can be seen, the sample tube is filled with the substance. طيب. If light passes again through the analyzer prism without any modification to its rotation, then the substance is optically active. تمام? Yeah, this is basically it. The object will be considered to be chiral. طيب. Otherwise, if it remains dark, then the object is optically inactive and the object is a chiral. طيب. Okay, we'll move on to I think the calculations part of the topic itself. طيب. Now, what happens is, what happens is, now, in order for us to find out whether the optically active what type of optically active substance that we are using, because it could be used as an identification method of the substance itself, we can rotate back the analyzer prism until there is no light passing through. تمام? طيب. Now this angle at which we rotate until there is no light beam passing through is called the observed rotation. تمام? This applies to only optically active substances. Is everything clear so far? Do you have any questions before I continue? And we're almost done. The next few topics are going to be quick and easy.
Mumkin they get us a question in the exam and they give us a specific substance or we have to think if it's chiral or achiral. ولا لا, they wouldn't do this.
If it is optically active, they can ask you that they've put a substance, okay? They've put a substance, حطوا substance جوا sample tube, okay? It allowed light to pass through after the light has been blocked. What do you consider this? Is it optically active or is it optically inactive?
Optically active.
So it is optically active, and optically active substances are chiral substances, صح?
Yeah.
So that's basically it. I honestly don't remember any questions exactly related to the polarimeter, but I remember that there was one calculation question. So don't stress about it. Just understand the concept itself and everything should be fine. Especially the equation. We'll come to the equation soon. It's the next slide.
Okay, but can I ask a question?
تفضل.
I hear something about D and L. Is this related to R and S?
D and L اللي هو
Dextro and
dextrorotatory و levorotatory. No. طيب هلا we'll talk about them but there is no relationship between them. They are two separate concepts and they are not related at all. طيب يعني whether it is an R or an S doesn't determine whether this is dextro-rotatory or levo-rotatory. طيب تمام.
Okay.
طيب so when it comes to the calculations related to the polarimeter, okay, now we've said that without the substance, without the optically active substance, assuming that we're putting in an optically active substance, the field of vision or the field of view, or there would be no light passing through the sample tube, and the sample tube would be completely dark, صح? طيب. So once we put in the optically active substance, we should have light passing through again. The field of vision should be visible again. طيب. Now, in order for us to determine the angle, we'll have to move the analyzer prism again. صح ولا لا? طيب.
Yes.
And this angle that we'll keep on rotating should give us back the dark field of vision. طيب. Once we obtain this dark field of vision, the angle that we calculate or we measure is called the observed rotation. تمام? This is the observed rotation. And the observed rotation is equal to the number of degrees that the optically active substance is rotated the beam of plane polarized light. تمام? Now, as we've mentioned, it either could be dextro-rotatory or levo-rotatory, and it's usually denoted by the plus sign or the minus sign. If it is dextro-rotatory, it means that the optically active substance will rotate the beam of light. The analyzer that we have used has been rotated clockwise, so the optically active substance is said to be dextro-rotatory, and if the analyzer prism, which is at the end of the sample tube, is rotated counterclockwise or to the left, the substance is said to be levo-rotatory. طيب. Now, there are certain factors that affect the observed rotation. What do you guys think are these factors?
Length of sample tube.
This is one thing. The length of the sample tube. Again?
The concentration of the substance.
The concentration of the substance, the number of molecules. طيب. What else?
Temperature.
Source of light.
Not the source of light, but we can say the wavelength of the polarized light itself. طيب. The wavelength. تمام. Finally, the molecular structure of the substance. طيب. We'll move on next to اللي هو finally over خلاص. Again, we have discussed the factors that affect the observed rotation, the molecular structure, number of molecules or concentration, length of the sample tube, wavelength of the polarized light, with temperature. Now, just a heads up, the wavelength, they usually use a certain lamp, which we'll talk about. So just to keep everything standardized, and the temperature at which they perform the experiment is usually room temperature. طيب, which we'll discuss over here, اللي هو specific rotation. Now, specific rotation, just a quick info about it because it has to do with just one equation. The specific rotation is a standardized test, or a standardized version of the observed rotation. لأنه the observed rotation at the end of the day is under many factors that we discussed. So we have to create something that is standardized, something that we can base our results on. طيب. And this specific rotation is a characteristic physical property of the substance. طيب. How do we calculate it? It's basically just only this part of the equation itself. It is the number of degrees اللي هو observed rotation, وعندنا length of the tube, وعندنا concentration. تمام. The temperature over here would always be at room temperature. Well, wavelength is always, usually most of the time, would be a D9 sodium vapor lamp وهي الويفلينث تبعه. تمام؟ وشو اسمه؟ I think that's basically it for اللي هو optical activity. حكينا length. طبعا length, always remember it's measured in decimeters. The concentration in gram per milliliter. والtemperature and اللي هو wavelength or whatever, these are يعني شو اسمه degree Celsius. wavelength اللي هو nanometers شو اسمه الألفا أو اللي هي observed rotation is in degrees. طيب, moving on. Achirality and optical activity. I'll go through it quickly. Now we've mentioned that a chiral substance is optically inactive. طيب. And this is usually because there will be another, for each achiral molecule, there will be another achiral molecule, which is a mirror image of the first one. طيب. That will rotate the plane of polarization in an equal amount in the opposite direction. طيب. So virtually no polarization will take place. طيب. Do you understand this?
Yes.
طيب. So virtually there will be no plane of no polarization taking place. Now, one thing that you people have to note is that the degree of rotation when it comes to chiral substances, the degree of rotation will always be the same. طيب. And it isn't a property. It isn't what we call a chiral property of the chiral substance. طيب. What is actually the chiral property of the substance is the direction in which they rotate plane polarized light, whether it is dextrorotatory or levorotatory. طيب. And this we'll discuss this in the next slide over here. طيب. اللي هو chirality and optical activity. Now, generally, chiral substances are optically inactive. طيب. Why do you think اللي هو racemic mixtures wouldn't be optically active? طيب, before we
Because the
move on.
enantiomers rotate the polarized light in the exact opposite direction, so they cancel each other out. So overall,
طيب.
it's optically inactive.
So the main reason is because the in racemic mixtures, enantiomers are present in equal amounts. صح ولا لا؟ طيب, so at the end of the day, طيب, the شو اسمه, the magnitude of polarization will be the same, and the direction of polarization will also be the same. So visually, we'll have no optically active substance or no kind of rotation taking place. But in reality, there is polarization that is also that is actually خلينا نحكي rotation that is actually taking place. طيب, as long as طيب, we have only a single enantiomer of a chiral molecule, we'll consider this chiral molecule or substance being used as optically active. أو in the case of where the ratio of a pair of enantiomer is not equal. So let's say it is equal to 20 to 80. Okay, then optical activity will be observed, and then the substance would be said to be optically active. طيب. Okay, we've talked about this part of the slides, which is basically اللي هو the number of degrees is not a chiral property. Again, whether it is 10 degrees or 50 degrees, this is not a chiral property, but the direction in which the plane polarized light is rotated is the actual property. طيب. And as I said, again, there is no relationship between the RS convention and the sign of our rotation of direction of rotation. The direction of rotation. طيب. This is excluded. طيب. It's either positive or negative. This is a note or what we use, the symbol that we use. Anyways, طيب. We'll take a quick example. طيب, R-lactic acid, whenever it's converted to its methyl ester, the configuration itself, the RS configuration, it never changes. It will always be an R. طيب. And this is because we haven't really changed much about the ligands attached, يعني priority when it comes to priority. But when it comes to its optical activity, it becomes the opposite. طيب. So this proves there is no actual relationship between the RS convention and the optical activity of the molecule. طيب. Moving on. One of your friends just a while ago mentioned that it has usually when it comes to optical activity, it has a lot of settings when it comes to biological activity. صح? And this is something that we'll discuss now. Basically, when it comes to enzymes, let's say, for example, the enzyme lactic acid dehydrogenase, it will always only oxidize dextrorotatory lactic acid to pyruvic acid, but it will never oxidize levorotatory lactic acid. Okay, so this proves the specificity of enzymes to the point where it will consider optical activity. okay, and شو اسمه. And this also mentions the fact أو اللي هو one of the properties that chiral molecules will have different interactions with other chiral molecules. So one enantiomer of a pair wouldn't react the same with another enantiomer of another molecule. طيب it will be totally different reactions. طبعا I'm sorry guys if I'm moving too fast, but it's just because of the time that I have to stick to the time limit. Anyways, is there anything that you guys don't understand? Just before we move on. طيب السكوت على معروضة. طيب. Okay, so basically, as I mentioned, one enantiomer may be used as a drug, whereas the other may be ineffective. There is an example now. I don't think you have to memorize any of these examples. They are just for your basic on knowledge. طيب, just give them a good read and go over them quickly and have a basic understanding of what's basically going on. طيب. One enantiomer may be toxic, the other may be harmless. One may be an antibiotic, the other may be useless, and so on. طيب. Okay, so basically the Fisher projection. Fisher projection is another way to represent a molecule, another way or another diagram. طيب. It's quite simple and it's a two-dimensional formula basically. طيب. There isn't really anything that is special about it other than it helps us look at three-dimensional formulas in a two-dimensional manner. طيب. So basically, as I mentioned, it's a type of two-dimensional formula of a molecule used to represent the three-dimensional configuration of stereogenic centers. طيب, what do you think are the features from what you can observe over here? So what's so different about Fisher's projection when it's compared to, let's say, a wedge and dash projection?
It's more of a 2D projection.
Again?
It's more of a 2D projection.
طيب, one thing. طيب, it's more of a 2D projection. What else? Anything?
And
طيب.
it doesn't have
The
any
wedge,
wedge.
yeah, the wedge
Again?
lines are usually horizontal,
Okay.
and then the dash are vertical.
طيب, that's perfectly it. That's basically it يعني, for the features. يعني. And one more thing to mention is that the cross link in between the vertical and the horizontal lines will always describe the carbon atom, اللي هو stereogenic center. طيب. Other than that, it's just another way of drawing the wedge and dash, and they're just basically overcomplicating things, honestly. Anyways, طيب, now for the features, we mentioned that the C for the chiral carbon atom or chiral center is omitted, represented by the crossing point of the horizontal and vertical lines. The horizontal lines will connect the stereogenic centers to group that project above the plane of the page, while vertical lines will project below the plane of the page. طيب. Interchanging between any of the two groups that are present on the lines will always give rise to another new enantiomer. طيب, we'll move on. Now, applying the Fisher projection, it's basically the same steps. We'll just have the lowest priority group in on one of the vertical lines, طيب, or one of the vertical arms of the projection, and then we'll just apply what we've already known about the RS convention. Priorities, then determine whether it is clockwise or anti-clockwise or counterclockwise. Then we determine whether it is an R or an S convention. طيب. Now, if one of the lower priority groups is on the horizontal arm, we'll just move on to rotate we'll rotate three of the groups. So basically the CL would move towards the CH3 position, CH3 towards the H, and the H towards the CL position. Is that clear?
Yes.
Okay, and it will directly give us whether it is an R or an S. طيب, for this one, it's pretty obvious. It is an R convention, صح? And I think it's clear because they've already made the priority and everything. طيب. But I'll leave you guys with something to solve at the end with an answer key. I was supposed to be solving it with you today, but time again. This chapter is really long, honestly. طيب, we'll move on. طيب compounds with more than one stereogenic center. We're almost done. خلاص مش ضايل. طيب. So basically, what are compounds with more than one stereogenic center? طيب, what's so special about them? طيب, I'll talk quickly about them. Basically, we'll be discussing diastomers. طيب. What are diastomers? What is your idea of diastomers? From the name itself, yeah.
Two
They
stereogenic
can have
centers.
more than one stereogenic center.
Okay,
Two or
so
more.
they basically have more than one stereogenic center. طيب, this is one thing. What else is يعني شو اسمه? What else is special about diastomers?
They are non-mirror images, non-superimposable.
They are non-mirror images of one another. Okay. But they can be superimposable and لا, they cannot be superimposable. طيب. At all, because they are شو اسمه? They are not mirror images in the first place. طيب. So basically, diastomers, we've mentioned that they are not mirror images of one another. They have at least at least two stereogenic centers or more than one stereogenic center. طيب. One thing to put in mind, and I'm stressing about this, and keep it, this will help you identify diastomers from regular enantiomers. Okay, whenever you're comparing two diastomers, you'll always find that one of the stereogenic centers that are present will always be the same. طيب. One of the stereogenic, and I'll show you an example. طيب. Other than that, that's basically what is a diastomer. Okay, we've mentioned that they are non-mirror image stereoisomers. They have the same configuration at one or more centers. This is one very important point that you can use to differentiate between diastomers and other types of stereoisomers. And in order for a diastereomer to exist, a compound must have at least two stereogenic center. Now, does it mean that a compound with two or more stereogenic centers, does it mean that it can't have enantiomers? This is not true. It can have enantiomers and it can have diastomers. It can have both. Okay, and we'll take this example, which is 2-bromo 3-chlorobutane. Okay, basically, now the RR 2R3R شو اسمه? Okay, I'll just write it down. 2R 3R 2-bromo 3-chlorobutane, and 2S 3S 2-bromo 3-chlorobutane are enantiomers of each other. طيب. But looking over here, when it comes to 2R 3S, if we ever take, let's say, these two compounds over here, these two enantiomers separately, they'll become diastomers. طيب. One point to keep in mind is that the 3S on both groups is the same. And basically, they have the same array on carbon number 3, but they differ at carbon number 2. طيب. Do you understand what I'm trying to point at? Or should I explain it further? Can you hear me, guys?
Yes, we can.
We are understand.
طيب, do you understand or should I repeat it?
We understand.
طيب. I'll just repeat it for good measures. Basically, what's happening is that 2S, okay, I'll just write them all down. 3R. If I was ever to take this enantiomer over here and this enantiomer, comparing them, they look like diastomers. One reason is that they are similar at one of the carbons. They have a similar convention, or the same convention, not similar, the same convention, but they are different at carbon number 2. And so this will conclude us to saying that these are diastomers. Right? Same would apply for any other two enantiomers separately. At the end of the day, since we have two stereogenic centers, we'll have four different stereoisomers, a total of four stereoisomers, and a total of two pairs of enantiomers. If we were ever to take any two enantiomers from the different pairs, we'll find out that they are both diastomers. طيب. If I was to take 2R and 3R and compare it with 2S and 3R, the 3R, the carbon number 3 will have the same array or same configuration, but the carbon number 2 will have a different configuration. Anyways, this is basically diastomers. It isn't that tough or complicated. And we'll move on to their properties, and the properties are honestly quite simple. طيب. First of all, we've mentioned that diastomers are not mirror images of each other. طيب. And so, since they are not mirror images, they may differ in all properties, literally chiral or achiral, whether that be either melting points, boiling points, solubilities, their optical activity, whatever. Literally, all the properties they'll differ in. طيب. Because they are not mirror images of each other, and so we'll usually treat them as two different chemical substances. تمام? And when it comes to calculations of numbers of stereoisomers, we can use these two formulas. They are simple. Just to find out the total number of stereoisomeric forms, or the maximum number of stereoisomeric forms that a compound could possibly have, you'll just have 2 to the power of number of stereogenic centers. To find out the number of pairs of enantiomers, you'll just divide this total by 2. طيب. But there are some exceptions. There are some structural features that will reduce the actual number of isomers, and we'll discuss them in meso compounds, which is just before the final topic. Now, when it comes to meso compounds, what are meso compounds? What do you guys know about them?
They have a plane of
compounds that have multiple
They have plane of
stereogenic
symmetry.
center,
Okay.
but they're achiral.
Right. So basically, they have
Identical
plane of symmetry.
molecules.
Again, just one by one.
Identical molecules.
Okay. What do you mean by identical molecules? And what's the basic concept?
Referring to the plane of symmetry that both molecules are the same.
It isn't. At the end of the day, they are the same molecule. They are one molecule, sorry. But exactly what you've mentioned is correct. They have a plane of symmetry. If we were ever to cut the molecule in half, طيب, the molecule would be able to fold in itself and form, or the molecule would have two mirror images of itself. صح ولا لا? طيب, this is one point. And so we conclude, since it has a plane of symmetry, the molecule is a chiral. صح ولا لا? طيب. And in definition, a meso compound is a chiral diastomer of a compound. طيب. It's quite simple, and we have a special example that we'll have to discuss, and we'll talk about it soon. Quickly, just to have a quick overview of it, it's quite simple. طيب. Meso compounds are achiral diastomers of compounds with a stereogenic center. Its stereogenic centers have opposite configurations. طيب. They're optically inactive and have a plane of symmetry and have superimposable images. طيب. Is it clear? You can see this in this example, which is the 2,3-dichlorobutane. If it is in the RS convention or an SR convention, it's basically the same mirror images of each other. They have a plane of symmetry, and so we call them a meso compound. But if they were in RR convention, 2R, 3R, they are enantiomers, and we'd consider them as being chiral. Is it clear?
Yes.
طيب. Can you, first of all, for this compound, one second. For this compound, can you tell me where the stereogenic centers are?
The two
Third and
CHs.
fourth carbon.
So it's basically this one and this one, صح? These are the two stereogenic centers. But is it can we say it is an actual regular enantiomer?
This is a meso compound because it
This
has
is a
plane
meso
of
compound.
symmetry
Okay.
vertically.
Again?
Because it has a plane of symmetry.
It has a plane of symmetry which goes right in the center, صح? طيب. So this plane of symmetry would cause this compound to be a meso compound. صح? It's a achiral diastemer because it has, first of all, two stereogenic centers. It's achiral because it has a plane of symmetry, and so we'd consider its optical activity to be inactive. تمام? And this compound has been useful in the past to be able to differentiate between different types of enantiomers and determine their convention. The reason behind that is that it has only three stereoisomers. تمام? It only has three stereoisomers. One of them is the RR, one of them is the SS, one of them is the meso compound, is the RS. This is basically tartaric acid. طيب. As you can see, it doesn't have any optical activities when it is in its meso form. The melting point is different. And yeah, that's basically it about tartaric acid. You just need to understand that it has a plane of symmetry in the meso form whenever it is in the 2,3-RS convention. تمام? We'll move on to the next topic, which is reactions. طيب, and this is the final topic. طيب, basically for the reactions there are generally only two rules that you need to understand and apply. Once you apply them, everything should be simple and straightforward. طيب. So basically for the first rule, rule 1, when chiral products are obtained from achiral reactants, both enantiomers are formed at the same rates in equal amounts. طيب. والproduct that we obtain is a racemic mixture. طيب. A mixture of equal amounts of two enantiomers. تمام? This rule is quite simple. So as long as you're obtaining your products from achiral reactants, the chiral products are from achiral reactants. طيب. Both enantiomers will be formed at the same rates and equal amounts. طيب. We have an example. Okay, this example is from the book. طيب. What do you guys think is the reason behind this? And why do you think we have equal amounts of a certain enantiomer being produced?
Because they are meso?
No. Any
Because
other
there's
reason?
equal positivities for equal possibilities for it to bind to the carbocation.
Yes, basically what's happening. طيب. Now this is basically electrophilic addition. I think you've taken it in chapter 3. طيب. Electrophilic addition of acids. What's basically happening is an electrophilic attack, which is occurring by the proton over here, breaking the bonds, the double bond, and creating a positive cation, صح ولا لا? 2-butyl cation, carbocation. And then it would attack the Br minus to form the compound that we're looking at. طيب. So basically what's going on is that we cannot actually determine just say that the rate at which the attack will form an S convention would be higher or lower than an R convention. The formation would be an equal rates. طيب. Because there is generally nothing restricting or no factors playing in whether S would be produced more than R. طيب. Do you get what I mean? There is no other external factors. We'll see this in a different scenario, which is rule number 2. There is certain factors that will affect the rate at which certain products are formed, chiral products. But basically, over here, there are no factors, and the attack will happen consistently, producing at an equal rate, producing two equal enantiomers. A racemic mixture, basically, equal amounts of the enantiomers possible. Yep. So this is one rule. So as long as we're talking about a product, a chiral product that has been obtained from achiral reactants, both enantiomers formed would be at same equal amounts. The product would be a racemic mixture. طيب. The second rule is when a reaction takes place with a chiral reagent reacting with an achiral reagent. So basically chiral with an achiral. طيب. This will lead to the creation of a new stereogenic center, and this leads to a di-stereomeric products at different rates and unequal amounts. طيب. We'll quickly take this look at an example, but what they're trying to say is the product will be a diastereomeric product, but we wouldn't have two diastomers of equal amounts. The amounts would be different, and the rates at which these two products or multiple products produced will be different, usually two products. طيب. There is always the creation of a new stereogenic center which causes the production of a diastomer. طيب. We've mentioned that a diastomer will always have, diastomers in general will have one same stereogenic center, while the other, or at least one, while the other stereogenic centers will always be different. تمام? طيب. So what's basically happening over here, we have 3-chloro-1-butene, which is reacting with HBr. طيب. We already have one, this is basically our stereogenic center, reacting with our achiral molecule. طيب. And we'll have two stereogenic centers produced. طيب. This is the new stereogenic center. This is old, the original one. طيب. Looking at the Fisher projection, we can determine that 3-chloro-1-butene that we were dealing with was an R convention or R array. طيب. Whenever it reacted with the HBr, we have two possibilities. طيب. What do you think of those two compounds would be created in greater amounts? And which compound of these two compounds would have the greater concentration? By the way,
Can you repeat?
Okay, which of those two compounds, طيب, the products, would be created in greater concentrations? We've mentioned that the diastomeric products of such reactions would have unequal concentrations produced at unequal rates. What do you think would be created in higher concentrations of those two products?
The first.
And why do you think is the first going to be created in higher amounts?
I'm not sure, but I think it's the most stable when we talk about the conformation.
When it comes to stability, they're both attached to the same carbon atom in both compounds. صح ولا لا? They're basically attached to carbon, I think, number 3. Oh, sorry, carbon number 2 in this case, because they're attached to the same carbon. But what is actually happening is that the Cl, it has to do with the density of the electron cloud around the Cl atom. The chlorine itself is quite a large atom in comparison with the hydrogen atom. So it would just cause some kind of, let's say, repulsion. It will make the space for the Br to fit in a lot smaller and a lot difficult. So if they were to be in S convention, if the Br was to be in the S convention, it will be a lot more difficult for this form to be created, this one over here. And so this product over here, which is 2R3R2 bromo 3-chlorobutane, would be created in higher amounts, because the hydrogen over here wouldn't create of the same effect as what is occurring over here with the chlorine. So do you get this idea? Or it's for your own general information, and I think there was some questions that might rise up. I'm not sure. Unless I'm wrong, I'm just confusing things. Anyways, that's basically it for the chapter itself. This is the whole chapter. I tried to cram it as much as I could in under an hour, but I failed miserably. And any questions? Do you guys have any questions? Anything that you don't understand so far?
Can you repeat the first one, please?
Which is rule 1?
Yeah, the one at the top.
Right, okay. Okay, rule 1, again, it mentions that whenever we have a chiral whenever we have a chiral product, okay, created from achiral reactants, this chiral product would always be a racemic mixture. Okay? Do you understand?
Okay.
Yeah. So basically what's happening, let's say over in this one, Okay, in one butene, whenever it reacts with HBr, this is basically an electrophilic addition reaction. طيب. It will create for us a stereogenic center at carbon number 2. صح ولا لا؟ طيب. So whenever the attack happens, طيب, can you actually determine whether it will be an S or an R convention? يعني whether R would be more than S or S would be more than R? You can never tell. Because there is no factor affecting the rate at which the BR would be attacked by the carbocation, since this is an electrophilic attack. طيب. What you only need to understand, طيب, just so we don't overcomplicate things, the mechanism itself is quite complicated, honestly. But what you have to understand, a chiral reactance, طيب, a chiral reactance giving chiral products will always give racemic mixture. Clear? This is what you need to know, basically, for the exam. Do you understand or?
Thank you.
Tamam. Any other questions just before we end the session?
Can diastereomers ever be conformers?
Diastomers being conformers. طيب. Okay, when we look at the structure of a diastomer, طيب, يعني what's at the end of the day they are basically alkanes, صح ولا لا؟ أو if they were to be alkanes, يعني what is stopping them from actually becoming a conformer? And we have certain examples in the book, but I honestly haven't put them in the PowerPoint because I was trying to keep it concise. Whether it becomes eclipsed or staggered, صح ولا لا? So conformers are possible in certain situations. تمام? But they'll never ask you, I don't think they'll ask you whether this is a conformer, يعني, is this a diastomer and a conformer or not? Is it clear?
Yes, thank you.
خلاص. طيب, what else? Any other questions?
I have a question.
Good.
When the product is a racemic mixture, so the racemic mixture is a chiral or chiral?
Again?
The racemic mixture is a chiral or chiral?